COMARL seminar, virtual seminar. Yeah, so as Shaigan just said, we will be recording this talk as well as streaming it on YouTube. So if you are not comfortable with somehow appearing on such a video, please turn off your own video. Also, please mute yourselves such that we don't get any background noise during the talk. And well, I guess that more or less covers those logistics. During the talk, we will use the normal chat icon, so this text balloon that says chat for everyone, for clarification questions. I will monitor this chat, and then if you type them there, I can interrupt Brano to ask for clarifications. If you have regular questions for the end of the talk, then please post them under this activities. So if you press the icon with the shapes and then Q&A, there we can pose questions, and then people can also vote for these questions. So you can just put in your questions there throughout the talk, and then people can already read them and see whatever they find interesting. All right, so that covers that. I suppose we will get started. So I'm very happy that today we have Branislav Bosansky as our speaker. Branislav is affiliated with the Czech Technical University in Prague, as well as Avast Software. And I've known him for some time now. Branislav has been doing some really nice and interesting work in the area of stochastic games and other game theoretic approaches. His background is not in reinforcement learning per se, so he indicated that if there's somehow terminology that is a bit different, or can use some clarification for this crowd, don't hesitate to ask for clarification. He's happy to talk. And yeah, that's it. So today you will talk about solving dynamic games with imperfect information. And so, Branislav, yeah, take it away.
Yeah, thank you very much. Thank you for the invitation and the opportunity to talk about our work on dynamic games. So this work and the collection of algorithms that I'll be talking about is a joint work, and I have a great opportunity to collaborate with many people. So mainly it's Karel Horák, because the core of what I'm going to talk about today is his dissertation thesis. But there are also other PhD students and postdocs and other collaborators with whom we have worked together on some partial questions related to all these algorithms. So what is the talk going to be about? So I will start with some motivations and some assumptions, because we are not able to solve general partially observable stochastic games, so we have to restrict ourselves to some reasonable subclasses of these games. And I think it's good to have some motivation whether these subclasses make sense, whether they are practical. So I will spend some time on the motivation and discussion what we are really solving, what kind of interactions and games we are really solving. Afterwards, I will introduce the two main subclasses of the partially observable stochastic games that we are solving, and I describe on a high level the variant of the search algorithm that we have for these kinds of games. And what I would love to conclude with and finish with is sort of a plea or call out for help and collaboration, because as Franz mentioned, my background is not really reinforcement learning per se, and I believe there is a huge opportunity for leveraging the recent findings and the recent methods of RL in in the framework and the schema of the algorithm as we design it right now. So hopefully you will be able to see how the recent methods can be useful and applied also to the partially observable stochastic games. So let's start with the motivation and some of the main assumptions. So in our work, we typically use security problems as a motivating example. So one of the main example is imagining that the scenario is about attacking and protecting a computer network. So we have, for example, some attacker that is trying to infiltrate a computer network, and we have a defender, be it admin, be it autonomous defending system, that is trying to prevent this attack from happening. Besides security motivation in computer networks, it can also be physical security, so allocating resources to protect targets and so on. The main reason why we are using these kinds of example is that they shape the assumptions that we use for our games. And one of the good example is that in security, the game is really competitive. So we have sort of clear sides, we have clear attacker that is trying to, for example, steal some information about credit cards, about private data, and we have a defender that wants to prevent this from happening. So there is a clear competition that helps us to motivate and to define the interaction and the scenarios as games. In these kinds of scenarios, there is typically a sequence of actions required before the goal is reached, or for example, the attack is completed, because the attacker needs to, for example, send a phishing email or exploit some software vulnerability. So the games are typically sequential or dynamic. So this is another reason why we are using these examples. Then there are unobservable actions. So players can or agents can execute some actions in the environment, and the opponent cannot really observe that some action has taken place. The players can observe only observations that are generated, for example, some alert in the system, but the actions are directly not observable. And this is in contrast, for example, with many board games, where typically in board games you have observable actions, because when people are playing board games, they typically need to know that some other player has made some action and what the action was. So this is another crucial assumption. Then the interactions can be actually quite long. So if we consider very slow stealthy attacks, they can take months or years. So like this motivates us to think about the games that have a very, very long horizon. So this is another reason. And finally, the game can be perceived as infinite, or even with infinite horizon, because even if we detect the attacker doesn't disappear. It's not really true that the game has finished, because the attacker will just use a different host computer, different credentials, and he will continue. They will continue the attack, right? So this also serves as another source of inspiration why we think that it's necessary to think about the long interactions, or not really having a strict horizon on the number of moves in the game. So what are the assumptions if we summarize it, and what is it that we are really looking at? So we are focusing on offline game solving for strictly competitive or zero-sum games, and we want to compute epsilon-ish equilibria, and we are considering infinite, indefinite horizon, and we're interested in practical algorithms. So what these bullet points mean is that for offline game solving, we really want to compute the approximate value of the game. So how the game would end if both players are following approximate optimal strategies. And we want to be able to extract these strategies. So we also want to have the strategies that achieve this value. And what we assume is that the game is known. So the rules of the game are known. All possible states or possible actions are known to both players. This is important because we believe, or I think, solving these games such that we have bounded error is complicated enough, even if the game is known. So, of course, another line of work can be investigating how all these algorithms can change if there is some unknown parts of the game. We focus on zero-sum games. Again, it's the simplest setting from the game theoretic perspective, and this gives us some guarantees that if we are solving these games and computing or approximating Nash equilibria, then the strategies that we want to extract to find are not exploitable, or exploitable only by some bounded number. As I mentioned, we want to compute epsilon Nash equilibria, and for an arbitrary epsilon, so we want to have an algorithm that converges to optimal strategies, and this also simplifies the comparison of different strategies, different algorithms, because we don't have to run tournaments and compare the strategies against each other. We can compare the quality of the strategies simply by computing best response against these strategies. So basically evaluate their exploitability. So this is one of the reasons why we are focusing on this part. We are looking into infinite or indefinite horizons, so we don't have strict limits on number of moves that the agents can perform in the game, and most of the time we are optimizing a discounted sum of rewards. So we have some discount factor that is strictly less than 1. However, in the most recent work, we also extended our algorithms to undiscounted sum of rewards. So we can also optimize the game if the discount factor is 1, but of course that requires some additional assumptions. We want our work not to be purely theoretical, so we actually implement and run the algorithms. Of course, the scalability would be one of the issues, and I will talk about it in the end of my talk. But we want to solve the games that are beyond toy examples, so the algorithms have to scale at least to moderately large games. And I think we are achieving this. And finally, we are trying to abstract from history-dependent strategies. So as we are focusing on games with very long or indefinite horizon, we don't really want our strategies to depend on full history. So we are focusing and restricting to games where this is not necessary. Okay, so these are our assumptions. This is like how we limit the scope of our work, and what are the partially observable stochastic games, and how we define them and how we reason about them. So as I mentioned, we have 2-player games. So we have player 1, that would be the maximizing player. Player 1 would be maximizing the expected reward, and player 2 is the minimizing player. And we have the definitions and dynamics that is basically very similar to POM-DPs or single agent sequential decision-making problems. So we have a set of states we have a set of actions, so we distinguish the actions of one player and the other player. And after choosing the joint action A1, A2 in some particular state, the transition functions that defines transitions to some other possible states that can be stochastic. And we have a set of observations and rewards that the observations that the players can observe, and the rewards that the players optimize. So I think at first it is important to answer the question why we are not really solving partially observable stochastic games in full. So why do we actually restrict to some special subclasses? And there are a number of reasons. There are theoretical results on undecidability of solving discounted POM-DPs. But one, I would say, nice argument why this is actually difficult is in something that we have found the term for as nested beliefs. So consider our game where we have like possible beliefs for the players that these players consider the states to be possible. So they have some probability distributions over the actual world states. And agent one or player one reasons about these possible states. So agent one has some belief, some probability distribution, and agent two also has this belief or similar belief over the possible state. And since this is a game and we want to solve the game from the game theoretic perspective, the agents also need to reason about what the other player is going to play. So since the transitions and rewards and observations depend also on the actions of the opponent, agent one has also needs also to reason about the possibilities and the belief that the agent two has. So agent one needs also to consider probability distribution over possible beliefs of player two. So what agent one thinks that agent two thinks about the true state of the world, and vice versa, right? So what the agent two thinks that agent one thinks about the true state of the world. And we can do this iteration over and over again, so we can nest these beliefs, and we will never stop. So it's sort of clear that to find optimal strategies in these kinds of games, we cannot really have these beliefs completely separated, and we need to be able to somehow limit this nesting and limit this reasoning that is necessary from the game theoretical perspective to answer the question, what is the optimal strategy and what is the optimal action to be played in some particular state of the game. So this is the motivation that leads us to some subclasses of dynamic partially observable stochastic games. So when we wanted to find out like what are these subclasses of partially observable stochastic games that we want to solve and we want to tackle, we basically had to resolve some trade-off because on one hand, we wanted to have subclasses of partially observable stochastic games where the agents can actually reconstruct the beliefs of the opponent. So we don't have this nesting, because every player can at every point like exactly know what is the belief of the opponent. So this is one sort of strong assumption. And on the other hand, we want these games to be practical, because recall that we have some motivation. We are doing this because we want to have some impact in a sense that these game models have to matter. We still need to be able to model the real world situation. So we term that the subclasses of partially observable stochastic games need to be practical in some sense. And we have identified two possible subclasses, and of course there are definitely many more. This is just something that we have discovered, and these are one-sided partially observable stochastic games and partially observable stochastic games with public observations. So in the first class of the games, we assume that one player has perfect information. In the second class of the games, we assume that the players both have partial information, so they have imperfect information, but all observations in the game are public, so known to both players. So let me dig a little bit into these two subclasses and provide an argument why do we believe that these are meaningful and practical subclasses of partially observable stochastic games. So especially in security scenarios, it is often very difficult to assess the knowledge of the attacker. So if we are designing some defense strategies against possible attackers, it's very difficult to estimate whether the attacker would be some random uninformed attacker that is just trying to use some scripts and doesn't really have the knowledge, the skill to perform a challenging and sophisticated attack, or whether there is, for example, the attacker can be an insider or well-funded external organization that has deep knowledge about the infrastructure and all the details, and can know basically many details about the security. So in this uncertain world, it can make sense to assume the worst, in a sense that we can assume that the attacker will actually be well informed and will have all the information about the defensive strategies and the defensive resources and infrastructure of the computer network. And still, we can be interested whether there exists some defense strategies that, despite having this well-informed opponent, whether there is still something we can do. So in terms of modification to our definition of partially observable stochastic games, we assume that player one, the maximizing agent, has the partial observability. So the maximizer has only limited observations about the game, and player two, the minimizing player, has the perfect information. So player two basically knows everything except future actions of player one. So player two doesn't know which actions exactly player one will be taking next. But other than that, all the past actions, all observations, and the actual true state of the world is known to player two. So these are one-sided, partially observable stochastic games. Next, I will talk a little bit about partially observable stochastic games with public observations, because this is a little generalization of the one-sided model, because of course, like, we understand that for many cases and many scenarios, assuming perfectly informed opponent can lead to very conservative strategies, or, for example, the game doesn't make sense at all. For example, if we model poker as a game with one-sided partial observation, then the partially observable player will not play the game at all because the opponent knows all their cards, so it doesn't make sense to play. So in some other games, we can like generalize the model and allow both players to have partial observations. However, we require some additional assumptions to be able to reconstruct the strategy, the beliefs of the opponent. So first assumption is that the state space is factored. So we have a private state space for each agent. We have states for agent one and states for agent two. And agent 1 or each agent is uncertain only about private states of the opponent, right? So agent 1 knows exactly which state it is in, but it doesn't know in which state agent 2 is, and vice versa. So this is first restriction. Second restriction is the restriction on game dynamics. So neither player can use their private information to refine their beliefs. So I cannot learn more about the position of and the state of the opponent by playing my actions without this fact generating some observation that would be known also to the other player. So to visualize this a little bit, I have this nice graph made by Karel. So we have 3 swim lanes showing which player knows which part. So each player, as I mentioned, knows their own private states, but they don't know the states of the opponent. They both make some action, and this action again is something only they can observe. However, these actions and these states generate some observations, and these observations are known to both players. And finally, the next state can depend on basically all the known information to the player. So the next state depend on their previous state, the action of the player, and public observations generated both from the player and the opponent. Okay, so this is like fairly general. So which games this schema covers, or these restrictions cover. So one example domain can be a patrolling with partial observations. So we can have a defender, which can be some patrolling unit that needs to like periodically visit the graph, and in the graph we can have some targets, and these targets are desired to be attacked by the attacker, and the attack takes several turns to complete. And the attacker is sort of outside the graph and waits for the right moment to attack. And if the defender is in these gray areas, the attacker doesn't know the exact position of the defender. However, if the defender is the patrolling guard is in these unclouded areas, both players actually know that this is visible, or this is the position of the patroller. So this is one like generalization of classes of games known as patrolling games. So we just added the possibility for partial observations, and these games can have some impact and applications in physical security. Another sort of nice game that fits into these definitions is the game of battleships, which most of you may know. Basically, you are trying to place and configure the battleships in the square board, and the goal is to hit and sink all the ships of the opponent before the opponent does the same thing to you. So this is also like these kinds of games also fit into the definition of partially observable stochastic games with public observations. So these are the classes of games that we are solving, and now we can move actually to the algorithms. So before I do, are there any clarifying questions?
Have none been posed so far, I think. So
okay,
pretty good.
Okay, so we can continue. So we have looked at solving these kinds of games, and I will start with one-sided partially observable stochastic games, and we have first formalized set of theoretical results then that allowed us to formulate, design, and implement the algorithm for finding approximate optimal solutions. So first thing that we have shown that is that there are quite strong similarities with single agent problems, so with POMDPs. And first key observation is that the value of the strategy of the imperfect information player is linear in beliefs over state. So this leads to a nice observation is that the value function of the game is convex. So this is the same as in the case of POMDPs, and we can approximate it from the we can approximate it as a piecewise linear convex function. So these results are they were known before, but we have summarized it and found out that this is one of the key reasons why we are able to solve and to design the algorithms for this class of games. And finally, this also leads us to be able to design and define the Bellman operator and use the dynamic programming algorithm for solving these kinds of games. So we can define the Bellman operator in a fairly similar way compared to the single agent problems. The main difference is that the expected rewards in the current step and then in the future step depends on the strategies of both players, where the player 1 is the maximizer and the player 2 is the minimizer. And the one-step strategies, so the strategies for this one update, this one step, assuming that we are in some specific belief point and we are investigating the strategies for this one belief point, then assuming that in the future steps, strategies that correspond to different alpha vectors are going to be selected. So in this one step, the strategies of player 1 are probability distributions over actions of this player, and strategies for player 2 are probability distributions over actions for each state that the player can or the game can currently be in, because player 2 can observe the true state of the game. So even though player 1 considers multiple states to be actually possible, player 2, for this particular belief, can condition also their strategy on the actual state that the game is currently in. One important distinction from the POMDPs is that the strategies can be randomized, and they really are randomized. If we really consider these games and investigate those strategies, these are really randomized, because taking only one action deterministically in some belief point will lead to exploitable strategies. So this is something that is different from say single agent problems, and we need to look for mixed strategies or strategies that are randomized. So how do we?
Sorry, Branislav, it looks like we have a question from Wojtek. He says, you mentioned alpha vectors, but perhaps not everybody is familiar with the terminology, and the slide doesn't contain any alphas. So I think it's a clarifying question.
Yes, so I will get to alpha vectors just in a second. So alpha vectors are basically the value functions that correspond to the value of strategy. So these are the hyperplanes that correspond to values of some particular strategy of agent 1. Any other questions?
Nope, that's it in the chat box.
Yeah. Okay. Cool, thank you. So how do we approximate the value of the game that we are seeking? So we have two approximate value functions. One is the lower bound value function, denoted v underscore, and these are the expected values for the strategies of player one, and against a best responding opponent. So these are corresponding to the alpha vectors I have just mentioned. And at the beginning of the game, we initialize these lower bound value functions, or this lower bound approximation, with the value of uniform strategy. So let's assume that the maximizing player will choose all the actions with like uniformly, with uniform probability, and the value that this strategy corresponds to against the best responding opponent is the value of the lower bound.
So there's another clarifying question.
Yes.
Asking about the x-axis in this plot, what the delta S denotes.
Okay, so this is the belief of player one. So this is the probability distribution over possible states in the game. So this basically represents the perspective of the maximizing player, the player one, and this player has some belief, and delta S represents this belief, these probability distributions over possible states. And the y-axis represents the expected value of the game, or expected value from the perspective of player one.
All right.
Clear?
So,
yeah. Okay.
I hope so.
Okay. Okay. Good. So you know, naturally, if we start basically with like the default strategy, that would be, I'm going to like randomly select an action in every situation that I get into. Like this is definitely a lower bound, and I can only improve my outcome from this strategy. So this is the lower bound, and we also like want to have some upper bound to drive our search, because this is sort of common schema in AI algorithms, where the upper bound, or basically the optimistic case, drives the search and tells you which actions are more promising that the agent should explore whether they are really good or not. So we have also the upper bound. So we are also estimating the value functions from above, and to get the initial values for these upper bound approximations, we use the values of perfect information refinement. So recall that the maximizing player is the one that has only partial information. So if we give this player additional information and we solve a perfect information stochastic game with concurrent moves, this will give us the values of these different perfect information games in the corners of the simplex of the belief space. So if we like assume that the players know that this is the current state of the game, and they will observe the state throughout the rest of the game, the value that we compute is definitely the upper bound on the true value of the game, because we simplified the game. We gave the maximizing player more information that it should have. So this is the way how we compute the upper bound, and we can form the lower convex envelope of all these points that we have in the upper bound, and this would be our V bar approximation of the value function. And now basically we perform the point-based updates similar to point-based updates in single agent POMDP type of algorithm with the modification that the updates are computed according to the Bellman operator that I have shown. So instead of searching for the best action, we are really solving the one-stage game, assuming that the players will then follow some other strategies from the that correspond to the value functions. And we are performing these updates separately for the upper bound and the lower bound. So if we have some belief, we can perform and compute the new value for this belief point according to upper bound, and add this point into the representation of the upper bound approximation, and the value of the function is, as I mentioned, the lower convex envelope of all the points that are in the upper bound. So the true value of this function decreases and change its shape, as shown on the figure. And similarly, we can add and perform the updates in the lower bound, and we are adding new alpha vectors that correspond to new strategies found by the algorithm. And since we started with a very simple strategy that was uniform, by changing that strategy and gaining more immediate rewards, we are improving the expected value of these new strategies. So we are increasing the lower bound. So this is with these updates, we are decreasing the gap between the lower bound and the upper bound, and eventually we are converging to the gap, to the point where the gap is lower than some desired epsilon in the initial belief point. So now we're certain that the true value of the game is within this epsilon interval for this initial belief point. So the algorithm is basically inspired, or what I have just described is basically inspiration by the heuristic search value iteration algorithm. So I'd say a classical algorithm for solving POMDPs. And as I mentioned, there are two key ideas. So one key idea is that the players are following their optimistic strategies. So when the algorithm is performing the self-play and is searching forward through different belief points that are reachable in this game, both players are choosing their strategies according to the optimistic outcome. And by that, I mean that the maximizing player is choosing the strategies according to upper bound updates, and the minimizing player is choosing the strategies according to lower bound updates. So both players are trying to steer the game into their preferred outcome, and this way we are exploring basically the part of the game, or those belief points where we expect that the players should find the true equilibrium point. So this is this is the high-level description of the algorithms. There is not much time to go into much details, but of course all the details can be found in our papers. And the main results are that we're able to approximate the value of the game within arbitrary interval, and we can even extract the strategies that achieve this value. So similarly to what I have just described for one-sided partially observable stochastic game, we can design or modify the algorithm also for partially observable stochastic games with public observations. And the main challenge is that due to the fact that both players have some belief, so there is no player that would exactly know the true state of the game. The shape of the value function is more complex, and it's now not a convex function, but it's a convex concave function. So it's convex in belief of player 1 and concave in beliefs of player 2. And our goal is not to find a saddle point in that value function, rather than we are really finding the value of this function for some initial beliefs. So this is the modification for partially observable stochastic games with public observations. So what are other variants that we have worked on over the years of this algorithm? Many of them are linked to the main issue with this algorithm, and that's scalability. So of course, as you may know, that these classical point-based algorithms for solving POMDPs are not really scalable, even for POMDPs. The same would be true also for partially observable stochastic games. And one of the there are several bottlenecks that we identified over the years that prevent us from scaling up. So first, of course, is the explicit representation of values of strategies and explicit representations of value functions. Then one bottleneck is the large state space. So if the game has many states, then the value functions are defined in very high dimensional space, and representing and working with this explicitly and exactly is very costly. And many of the steps of the algorithm require solving linear programs. So when we are performing the Bellman update, since we are really solving one-shot game, assuming that the future rewards are according to some linear functions, we are solving some linear program. And since we are performing forward search with forward updates and backward updates, we are solving a lot of these linear programs. So solving this computation is one of the limitations of the algorithm as we currently have it. And besides these updates or these point-based updates of the value functions, also computing the lower convex envelope for from the points that are representing the upper bound value function is also done by linear program. So these are one of the three problems that we face, and one or some of them we were able to at least partially address. So I will introduce or briefly speak about how we dealt with large state space, and in the next part I will briefly talk about removing the necessity for the linear programs.
So you have about 10 minutes left. So let me give you a bit of a warning that that you know.
Yeah, I think I'll make it. Okay, thank you. So what are the issues with large state space, or where we can encounter these large state space, or what does it mean to have a large state space? So let's assume again, going back to our motivation, and this is why I think it's very good to have these motivating examples. Let's think how the attacker actually attacks the computer network. So when the attacker enters the network, for example, using a phishing email, he takes control, or they take control over some host node, some host computer, and then they move laterally in the computer network by infecting other and taking control of other hosts. And they are not really moving from one node into another, but they are spreading. So they can control a larger and larger fraction of the computer network. And if you want to reason exactly about this, we would need to consider all the possible subsets of computers that are already infected. Similarly, if we are just thinking about allocating multiple defense resources to multiple targets, while assuming that the attacker can attack multiple times in a sequence, and we want to think and allow the defense resources to reallocate. These reallocations again induce exponential number of possible actions, because we need to consider whether resource 1 will move from target 1, and at the same time the resource 2 will go to target 3 or target 4, and so on and so on. So these are exactly the problems that we face when we are thinking about games with insecurity domains, and how we solved it. And this the solution is not like fully general, so we have the solutions for specific games. Is that we can, like, instead of using the domain for the value functions in the form of probability distributions over possible states, so we can change it to think and to use so-called marginal probabilities over possible like targets or nodes. So these probabilities can represent what is the probability with which some particular host in the computer network is infected or not. So instead of having these combinations and probabilities over these combinations, we can move to a much more compact representation and use and reduce basically the domain of the value function exponentially. So of course it's not straightforward that if we perform this projection that everything in the algorithm would still work, but we were able to show that for certain cases it actually does work, and the algorithm can be applied also to games that have such a compact representation of the uncertainty, and we can, thanks to this compact representation and this projection, we can scale to much larger games. For example, in this lateral movement game, from graphs and computer networks that represent from 5 nodes that represent a very small computer network, we can scale to 30 or 40 nodes, depending on the structure of the underlying graph. So this is one example how we tackled the scalability issues of our algorithms, and I would like to conclude basically with the future or next directions that I see as like possibility for new research. And what I would like to argue is that what we have actually done over the last years is like define some baseline algorithm for solving these kinds of classes of partially observable stochastic games. So I see it as a example of a tabular approach for these games, and now basically it's a good time to try to scale up using reinforcement learning and other methods that allow us to scale up and to replace the methods or the subparts of the algorithm that we currently have with recent results from the reinforcement learning. So again, recall the bottlenecks, and I mentioned that I will very briefly speak about the linear programs, and especially using the linear program for computing the lower convex envelope for the upper bound value function. So computing the true value, the true approximation, true value of the upper bound approximation of the value function is actually very costly. Like it can take up to 80% of all the running time of the algorithm. And for example, in POMDP HSVI, it's resolved by using so-called sawtooth representation. So instead of really having the true lower convex envelope over these points, every point is only like connected to the points in the corner, and the value for the upper bound is approximated as the minimum of all these hyperplanes that are constructed in this way. However, what would be even, I think, better, in my opinion, would be to use, for example, a neural network in a sort of very classical way as a function approximation for this task. So let's assume I have a set of points, and the goal would be to have a neural network that would like represent the lower convex envelope of these points. So we are actually exploring this direction, and what is like very nice is that the task is like quite specific, because we actually want to train a convex function, which has some nice consequences and impact on the structure of the neural network, and we can bound the error of the approximation, which is also like quite desirable, because like we are approaching the problem from the perspective that we still want to be to have guarantees on the performance, and we still want to be able to bound the error. However, there are some interesting challenges when we are exploring this avenue. So one is, of course, pruning outdated values. So like whether we can in an efficient way remove points that are basically no longer on the lower convex envelope, because if we keep training them or feeding them into a neural network, they're all, of course, like decreasing the performance, because they are not lying on the lower convex envelope. So we need to find an efficient way how to discard them. And it's also like the challenge of evaluating the impact of the error of the approximation, because the original algorithm really depends on the fact that if we select one belief and one direction for the forward search, there has to be some action connected to that, in a sense that after like exploring some part, we need to have guarantees that this part is explored, and what we have computed has some reflection on the either upper bound or lower bound approximation of the value function. So either the lower bound improved or the upper bound has decreased. But if we are using imprecise function approximation, then the whole algorithm can get stuck, because it will like forever, for example, explore the same beliefs over and over again. So let me conclude. What we have basically so far, and what we have designed over the last couple of years, is some algorithmically solvable variants of partially observable stochastic games. And we have now theoretically grounded baseline algorithm. And I believe there is a huge opportunity for like taking this algorithm as a baseline and trying to improve it so that the scalability can be pushed to limits, because of course with our game theoretic methods, we are unable to solve really large games. So finally, with like the implementation, we are working on like a new, very simple implementation of the HSVI algorithm for solving partially observable stochastic games. So we have it in Julia, and hopefully it will be released soon. And if you're interested in looking in this algorithm and looking in these kinds of problems, I'll be happy to talk about it more. And if you have questions now, I'll be happy to answer them as well. Thank you.
All right, great. Let me thank on everyone's behalf. So I think we have one question certainly already in the chat. So I can read it out if you want. It's by Rahul, and he asks, suppose that we don't have public observations and also have a very large problem, so an RL approach is needed. Do you feel it still makes sense to think about HSVI as a basis or just inspiration for solving such a zero-sum post G in combination with deep RL somehow?
Yeah, I don't know. Like the main reason why we have chosen the HSVI is really that it has like we were able to show the theoretical guarantees, and once basically we move from a subclass of games for which we know that the guarantees like apply. So I'm not certain whether the HSVI can like bring anything there. Maybe yes, because like technically it has this nice idea of having the optimistic estimation that drives the search and the anytime value for the best found strategy so far. So it's I would say very classical AI algorithm. So maybe it can be still like valuable, but I cannot really estimate how would that work like for like more general subclasses for which we don't have the theoretical guarantees that, for example, the strategies even exist.
No problem. Actually, the games I want to solve. Thanks a lot for the very nice talk, by the way, and hi, hope you're well.
Thank you.
I know the games that I want to solve, so maybe I'm going to shoot you an email and I can convince you to let me get you on a call and pick your brain about them at some point. But yeah, no, very nice stuff. Cheers.
Yeah, thank you very much. And yes, I'll be happy to talk. Yeah.
So I don't see any other questions yet. So let me perhaps ask one. So you talked about these POSGs with public observations, and so this reminded me a lot of these games that were considered in this paper from some time ago on zero-sum stochastic games with partial information by Gosh et al. Can you perhaps explain what the main differences are between these models? Does your HSVI approach now also apply to that category of games?
Yeah, I know which paper are you referring to, but I have forgotten the like exact assumptions that they were using. So
yeah, it's also some time for me, but the reason that I think it could be quite interesting is because so this paper that I had back in the days with the student Auke Wiggers, there we kind of showed that for a general zero-sum game, two-player zero-sum game, you could essentially convert to a special case of their model. So then if these approaches are applicable to that model, then it would imply that actually your solution approach might extend to even general zero-sum POSGs.
I don't know from like the top of my head. I would have to like go over their model, because I know that we were investigating that at some point and concluded that it's not entirely compatible, but I don't exactly remember the details, because I think that there was something that was not entirely directly applicable, but I don't remember the details. Sorry.
Yeah, no problem. So what I seem to remember is that this was kind of like the strategic equivalence of some sort of what I call a multi-agent POMDP, where so that's the type of model that somehow there's these joint observations, but you can somehow solve it in a centralized way. So the observations would be common knowledge indeed. But yeah, then in a strategic or a competitive setting, rather than what you would typically assume for a team of agents really optimizing, because then it becomes essentially a large POMDP. Never mind. So let's perhaps follow up on that. There's one more question here, and then perhaps we should move to wrapping up. Aurélien, is Aurélien still on the call? Do you want to pose the question yourself? Otherwise, I can also read it out. Let me otherwise read it out. You mentioned that you restrict the scope to zero-sum games and that you solve linear programs to compute the Bellman backups. What is the main difficulty when trying to solve general-sum games using specific LP algorithms designed for general-sum? Referring to Lancaster algorithm, for example.
Okay, thank you very much for the question. So like whenever we are, whenever I am thinking about general-sum games, I typically think about Stackelberg equilibrium rather than Nash equilibrium in general-sum games, mainly because of reducing some problems in the equilibrium selection problems. So without additional assumptions, if we have like multiple Nash equilibria, it's unclear like, which values should we propagate upwards. So we haven't really like investigated solving Nash equilibrium in a general-sum game. We have spent some time on looking into computing Stackelberg equilibria in stochastic games. And the thing is that it's a lot more complicated to compute Stackelberg equilibria in these games, because Stackelberg equilibrium, if I'm not sure whether you're familiar, so in Stackelberg equilibrium, the leader commits to some strategy, assuming that the follower plays the best response to this commitment. So from this perspective, it's again, very difficult to design sort of dynamic programming type of algorithm, because in some parts of the game you may want to commit to basically irrational strategies, so that you force the follower to play differently in different stages of the game. So it's not sufficient to propagate basically just one value for one, for example, belief point, but you need to propagate all the possible solutions that are achievable, and this significantly complicates the algorithm. It's possible, and like we have a version of algorithm for like limited classes of stochastic games, but it's not really practical.
All right. Well, thank you very much, Branislav. I suggest we wrap up. Yeah, so let me thank you again for a great talk. Yeah, I think we are planning to be back in 2 weeks, I think. But yeah, we'll announce on Twitter and on our emailing list as usual. So please make sure you join us next time. Yeah, thanks, Branislav. Thank you all for the interesting questions.
Thank you. Thank you all. Bye.
Bye now.